So power is one of those things that comes up over and over again in all different areas of physics, in mechanics, in forces of motion, which is mechanics, in electricity, even in space, when we're looking at stars, they have their own power called luminosity, but it always has the same definition. Power is equal to the rate of energy transfer. Now, in a previous video you may have watched, here we go. We know that energy transfer also equals work done. So there's a second definition we can use, and both of these are as valid as each other. Power is also therefore equal to work done, the rate of, sorry. That's a bit annoying of me. Anyway, there we are. So power equals the rate of energy transfer or the rate of work done. Now, this means we've got two equations that are essentially equivalent that we can use. Whenever you see the word rate in physics, it means divide by time. Think about when you're doing biology and think about your heart rate, it's how many beats per minute. In physics, our per time is always the second. So rate always means per second, which means we can work out this equation. If power is the rate of energy transfer, it means it's the energy per second or divided by time. Or I can write it as the rate of work done, the work divided by time. And I can use either potentially here. To be pernickety, you'd probably use this if you've got mechanical work going on, or even electrical work, and then this for other types of energy, but you're never going to get penalised for using one or the other. Now, the unit of power you'll have seen in the supermarket. If you go to the light bulb section in a supermarket or a hardware store, you see that all the powers of the bulbs are given by this symbol here, W, which stands for the watt. And the unit of power is the watt, which means I get my favourite question in physics. What is the unit of power? What is the unit of power? It's a question that answers itself, and me as a physicist quite sadly enjoys that. And we can break that watt down if we want to. If it's energy over time, then a watt is equivalent to a joule per second, because the unit of energy and work done is joules. We divide that by time in seconds. So when you see the unit of power as the watt, it means joules per second. And we can apply that here to these two light bulbs. So if you get a 40 watt light bulb, what that means is that each second 40 joules of energy is used, or it won't all be released because they're not 100% efficient, is used per second. So this light bulb will give off 40 joules of energy per second. This one, because it's a 100 watt light bulb, will give up 100 joules of energy per second is used. So this bulb, because it gives off more energy every second, will be brighter. And you've probably seen that with different wattages of bulbs. If you want to have a nice bright bulb, you buy a higher power bulb because it means it's giving out more energy every second. Now, the biggest thing you have to do with power is use the equation. So we've got a couple of examples here. Some of them are straightforward, some have got conversions in, and then one of them at the end is adding another equation in. So we're going to start with this one here, the simplest one. What power is required for an electric shower that uses 180,000 joules per minute? So we're going to use the equation P equals E over T. And we don't need to rearrange it because I'm looking for power. Now the energy is 180,000 and the time must always be in seconds. For this equation to work, because a watt is a joule per second, I must have the time in seconds. So a minute is 60 seconds. Now when I do 180,000 divided by 60, it comes out as 3,000 watts. Or you can write that if you want to as 3 kilowatts. You can write it either way. If you look at a shower, if you find like the label with all the information on, it will probably say something kilowatts because showers generally use a lot of energy. They're very powerful. So this is quite a standard power for a shower, hence the name power shower. Next question, how much energy will a 40 watt bulb use in 2 hours? So we're going to use the equation P equals E over T again. But I now want to rearrange it in terms of energy because I'm being asked to find out how much energy there is. So I need to take the T to the other side and I do that by multiplying. So E equals PT. And the power is 40 watts and the time, like I say, has to be in seconds. So 2 hours is 2 times 60 minutes times 60 seconds. So I do that sum and it comes out as 144,000 joules, which is a lot. but it's standard. This is the amount of energy that you're using every 2 hours if you've got a light bulb on. So they're pretty high numbers. That's why we use kilojoules quite a lot. You could write this as 144 kilojoules if you wanted to. Okay, the third iteration of this equation. How long does it take for a 1.2 kilowatt kettle to use 6,000 joules of energy? So we're now going to rearrange in terms of how long, which is time. So power equals energy over time. Therefore, this is the hardest one. These two can flip around. Now, the way I do rearranging is that I think about if it's on the bottom, it goes to the top, and on the top, it goes to the bottom. So I can write this as T equals E over P. And this is the one that most people get wrong, this rearranging. So the energy is 6,000 joules. And the power is 1.2 kilowatts. Now, because I've got this in not kilos, and this is in kilos, I need to change that. So 1.2 kilowatts is 1.2 times 1,000, which is 1,200, if you can do it in your head. So I do 6,000 divided by 1,200, or 1.2 times 1,000, and that comes out as 5 seconds. Okay, so we use a lot of energy all the time. Your kettle is probably on for a couple of minutes when you boil water. You're using thousands and thousands of joules of energy. So the final question here is the one that combines a couple of equations. So we've got, it takes 30 seconds for a crane to lift a 1-ton concrete block 20 metres into the air. What is its power? Now I'm going to write the equation down. I'm going to write it down as work done over time because it's going to help us later on. So we've got power equals work over time. Now I've got the time. The time is 30 seconds, but I don't have the work done. However, I have got 1 ton, which is a mass, and I've got 20 metres, which is a distance. Now I can turn this mass into a force by thinking about its weight, and I've got a distance, and I know that work done equals force times distance. So here I'm going to work out the work done. So the work done equals the force, which is the weight. Now the weight is going to equal mg for the force. So m is 1 ton. Now 1 ton is 1,000 kilograms. If we think about metric tons, and g is always 10 newtons per kilogram. You might use 9.8 or 9.81. My spec uses 10. So that's the force. It's the weight of that concrete block, and it's being lifted 20 meters into the air. So that's, I can put 20 there. So 1,000 times 10 times 20. The work done is 200,000 joules. Now I can put that into the equation. P equals W over T, so 200,000 divided by 30 seconds, and the power comes out as 6666.6666 going on. So I'm going to write it as 6667 watts. I'm going to round it up because I never write a recurring symbol in physics. So that's how to use the power equation and the definitions for power, which will come up over and over again in physics.